pH. As we have seen, water is amphiprotic. In pure water, a few molecules act as bases and a few act as acids. This produces some hydronium ion, H3O+, and some hydroxide ion, OH-, in the reaction shown here. This is called the autoionization of water and is one of the most important reactions in terms of its usefulness that we will encounter. The equilibrium expression for this reaction is Kc equals the concentration of H3O+ times the concentration of OH-. It is a specially defined equilibrium expression, and it's called the ion product constant for water. It is given the symbol Kw for water. At 25 degrees, Kw has a value of 1.0 times 10 to the minus 14th. The pH scale is defined mathematically as pH equals minus the log of the concentration of hydronium ions, or the concentration of hydrogen ions. Because the concentration of H3O+ is usually less than 1, the negative sign gives us positive values for pH, but also means that as the concentration of H3O+ increases, pH decreases. In pure water, the water equilibrium occurs, and the equilibrium expression for that equilibrium is Kw, whose value is 1.0 times 10 to the minus 14th. In pure water, we have an equal amount of hydronium ion and hydroxide ion. So, in pure water, the concentration of H3O+ is 1.0 times 10 to the minus 7th molar. So in pure water, the pH is 7.00. An acid has a higher concentration of H3O+ than pure water, so its pH is less than 7. A base has a lower concentration of H3O+ than pure water, so its pH is greater than 7. So an acidic solution has a pH less than 7, a neutral solution has a pH equal to 7, and a basic solution has a pH greater than 7. You will see other p scales that are defined in the same way pH is defined, that is, as minus log of that quantity. Some examples are POH equals minus log of the concentration of OH-. pKw equals minus the log of Kw. And pKa equals minus the log of Ka. There is a very useful relationship between pH and POH. Watch what we do here. Because the concentration of H3O+ times the concentration of OH- equals Kw equals 1.0 times 10 to the minus 14th, we know that if we take minus the log of both sides of the equation, we get minus the log of the concentration of H3O+ plus minus the log of the concentration of OH- equals minus the log of Kw equals 14.00. Or, in other words, pH plus POH equals pKw, which equals 14.00. This equation implies that as pH increases, POH decreases, and vice versa. This is an important simplifying understanding about pH and POH. The assumption here is that the solution is at 25 degrees Celsius. Here is a diagram that reflects the relationship among concentration of H3O+, pH, POH, and the concentration of OH-. To convert from concentration of H+ to pH, we take minus the log of the concentration of H+. To go from pH to the concentration of H+, we take 10 to the minus pH. Similarly, To go from the concentration of OH minus to POH, we take minus the log of the concentration of OH minus. And to go from POH to the concentration of OH minus, we take 10 to the minus POH. To go from the concentration of H plus to the concentration of OH minus, we use Kw divided by the concentration of H plus. And to go from the concentration of OH minus to the concentration of H plus, we use Kw over the concentration of OH minus. However, to go from pH to POH, or vice versa, we merely subtract from 14.00, that is pKw. To go from any point on the square to any other point, we simply follow the path. For example, to find the pH from the concentration of OH minus, we can do two things. Concentration of H plus equals Kw divided by the concentration of OH minus. Then pH equals minus log of the concentration of H plus. Or POH equals minus log of the concentration of OH minus, then pH equals 14.00 minus POH. This figure shows the pH of a number of common substances. Notice that foods tend to be acidic or just slightly basic. The very basic substances tend to be chemicals. How do we measure pH? There are two common ways to measure the pH of a substance. First is by using an indicator. These are used when we do not need to be overly precise or very accurate about the pH. An indicator is a substance whose color changes with the pH. It is usually a weak acid whose acid form has one color, while the conjugate base has a different color. One example is litmus, where the acid form is red and the base form is blue. Litmus paper is available, in which the paper has been soaked in a solution of either the acid form, red litmus, or the base form, blue litmus, of the dye. Red litmus paper will turn blue in base, and blue litmus paper will turn red in acid. The picture shows the range of the color change for a number of indicators and the two colors of the indicator. For example, methyl orange is red at pHs below 3 and yellow at pHs above 4.5, and will change color at about pH 3.8. If we want to tell more than just whether the solution is acidic or basic, or above or below a particular pH, we can employ a carefully selected mixture of indicators, which will have different colors in different pHs. These mixtures are often called universal indicators, because they will distinguish any pH. The second, more precise and accurate method is to use a pH meter. It measures the voltage generated by a special electrode. This voltage changes with the concentration of H+. The 7 common strong acids are HCl, HBr, HI, HNO3, H2SO4, HClO3, and HClO4. By definition, these are strong electrolytes and exist totally as ions in aqueous solution. For strong acids, the pH of a solution can be determined by using the concentration of the acid. For the monoprotic strong acids, the concentration of H3O+ equals the concentration of the acid, and the pH equals minus the log of the concentration of the acid. For H2SO4, the only diprotic strong acid, it is nearly, but not quite, true. The strong bases are the hydroxides of the alkali metals and the alkaline earth metals. These are also completely separated into ions. For strong bases, the pOH can be determined from the concentration of the base. If the base has only one OH minus, like sodium hydroxide, NaOH, then POH equals minus the log of the concentration of the base. If it has two OH minuses, like calcium hydroxide, CaOH2, then we need to multiply the base concentration by 2 to get the concentration of hydroxide ion. And POH would be equal to minus log of 2 times the concentration of the base. All acid dissociations have the same basic form, with the same basic form for the equilibrium expression. To compare the strengths of several acids, then, that is, how much each dissociates, we need only look at the values of their respective Kas. The larger Ka is, the more the acid dissociates, and the stronger it is. Note, however, that all weak acids have Kas less than 1, so all have more reactants present than products. Here is a table showing a few common weak acids with their structures, conjugate base, dissociation reaction in water, written in the Bronsted form, and the value of Ka. The table in the appendix at the back of your book has many more acids and Ka values.